Welcome everyone. Thank you for coming today. Today we are having Cristian Tabares, who is a PhD student here at the Institute of Fundamental Physics of the SIC. Cristian studied his degree in physics in the Universidad Autónoma de Madrid, and then did his master's degree at the in theoretical physics at the Complutense. Cristian has already done some work at ICFO with the group of Darik Chang, the group of theoretical and photonics, and now he's working here with under supervision of Alejandro González Tudela. And today he's going to talk us about variational algorithms in setups of waveguide-QED. So, Cristian, whenever you want.
Well, thank you, Carlos, and all the organizers for giving me the opportunity of telling you a little bit about some research that we have been doing recently these past months. And yes, as Carlos just told you, the topic of my talk, as you can see here, is waveguide variational quantum algorithms. So I would like to divide it into parts. Let me see. Okay, into parts. The first one will be a part where I would like you to introduce you to the topic of quantum simulation. So in general, we would like to answer two different questions. First, why do we do quantum simulation? And second, how we can do it. Okay, so we will discuss two types of approaches, the digital quantum simulation and the analog one. And then we will discuss the variational quantum simulation, which will directly be connected with the second part of the talk, in which we will focus in particular in waveguide platforms. Okay, and for those of you that don't know what is waveguide-QED, I would like first to introduce you to the topic, okay, of light matter interactions, and then with all of this already done, I would like to discuss the paper that we have recently published, okay, that was in the last slide, in which we introduce the topic of variational quantum simulation in these waveguide-QED setups. Okay. So with this in mind, let me just try to start motivating a little bit the thing, okay? So in general, we want to study quantum systems. That's the main topic of quantum simulation and also of my talk. And we want to study, for example, a single qubit. We have only two states, okay? So this is very easy to compute even by hand, okay? If we include a new qubit, okay, and let this qubit interact, okay, so we can have a superposition of these two states, four states. The Hilbert space grows, okay, but for a small number of qubits, this growing is not very problematic. The thing gets much worse when we include a big number of qubits, because the Hilbert space starts to grow exponentially with the number of qubits. Okay, so when we got n qubits, we got 2 to the n states possible, and as soon as n is around 50 qubits, this is intractable for most classical computers. Okay, so in general, we want to study quantum systems which are big. Okay, and big here means more or less 50 particles. Okay, we need to do something that goes beyond this naive brute force approach. Okay, so motivated by this, already in 1981, okay, Richard Feynman pointed out that, well, okay, nature is not classical. Okay, and if we want to simulate nature, the first thing that we could do is to do a quantum simulation of nature. Okay, and this is not easy because we can control classical computers very easily, but we cannot control quantum computers, whatever that are, whatever that means, that easy. Okay, but this is more or less the motivation. Okay, if the quantum simulator, the quantum computer already has these rules implemented, why don't you use it to do this quantum simulation? So the thing is that in general, the classical techniques to do simulation in quantum systems, such as, for example, tensor network techniques or quantum Monte Carlo DFT, cannot be applied to many systems of interest. For example, you want to study out-of-equilibrium systems, the tensor network approaches fall. You want to study fermions, the quantum Monte Carlo approach fall. Strongly correlated systems cannot be studied using DFT. So in general, systems that are very interested in quantum science cannot be easily understood with the current techniques that we have. So the idea of quantum simulation is the following. We have a quantum system, okay, and we, in general, introduce the rules that govern the behavior of this quantum system inside a classical computer. We perform the calculations, and then we read the properties concerning the quantum system. And the idea here is saying, well, okay, this is fine, but this in general generates an overhead that I don't want to pay. So what I would like to do is, instead of this, I would like to use a computer that is quantum by itself to study the quantum system. And this is what we do in general with quantum simulation. Okay, so the definition could say that quantum simulators are controllable quantum systems that we use to simulate or emulate other quantum systems. Here, controllable means that we can control its properties. That means that we can generate desired and specific evolutions, okay, that are not random. This way has been pointed out recently as a path to solve problems that could be intractable for current supercomputers, current classical supercomputers. That term that has been coined out as quantum advantage. Okay, and I'm sure that some of you have heard recently about this hot topic of quantum advantage, which will mean that we are able to do some specific computation with a quantum computer that cannot be efficiently performed with a classical computer. Okay, that means that for that specific computation, our quantum computer has an advantage over the classical computer. And as you can see here, that quantum advantage has been actually obtained. This is the famous Google experiment, okay, where they did something called a random circuit sampling, and this is also an experiment where they did something called boson sampling. And in general, okay, the problem with this is that although we have already obtained quantum advantage, this quantum advantage was only obtained for a specifically tailored task. In more or less, in a general way, we could say that the thing that they do here is that they generate distributions of probability that are very hard to reproduce classically, but that are natural in some sense to quantum computers. So they choose this specifically tailored task, and in that way they obtain this quantum advantage. So we may wonder if it is possible to go beyond to obtain a practical quantum advantage that it's useful for something. Okay, because well, in general, it has been pointed out that maybe some of these protocols could be used to generate random numbers, but they are not very useful. At least there are not very actual applications of them at the moment. I would like to obtain these practical applications of quantum advantage. So I really like this review here, okay, in which they discuss, the authors discuss that a natural playground to obtain a practical quantum advantage could be quantum simulation. Okay, so in this way, we will use these quantum systems to simulate another quantum system that could be very hard to simulate with a classical computer. And in particular, they point out that many of the most promising short-term applications of these quantum computers fall under this umbrella of quantum simulation. Okay, so this a big framework motivates what we would like to do. Okay, we would like to do quantum simulation. And the main goal of this quantum simulation will be to perform some kind of calculation that will be very hard to reproduce with a classical computer. Okay, so with this in mind, okay, I hope that more or less the topic is motivated for you, and you are already convinced that we need to increase the performance of current quantum simulators to finally reach this practical quantum advantage. But now we may wonder how we can do it. Okay, how is it possible to perform quantum simulation? And in general, in the literature, there are the two different kinds of approaches, and we usually establish this difference. First, we have the analog quantum simulators. Okay, I'm sure that most of you already know about them. And the idea with this is that we mimic a total Hamiltonian that we want to study using a controllable system. Okay, and for example, examples of these platforms are ultra-cold atoms in optical lattices. For example, the ones have Bloch-Zurück, also trap ions, or so neutral atoms in Twister arrays. And in general, the thing here is that we have a quantum system. For example, here, well, are atoms which are very, very cold, hence the term ultra-cold atoms that are trapped in some optical potential. Okay, so you got the atoms trapped, and you can modify their behavior, with, for example, lasers or whatever, and then those can move between the trapped sides. Okay, and in this way they interact under some Hamiltonian, and you expect to understand the dynamics of the given Hamiltonian using the Hamiltonian that the atoms use to interact. Okay, so in that way you mimic the Hamiltonian with this controllable system. Okay, so the idea, one of the most relevant advantages of this idea is that this type of calculations are more resilient to noise and errors. Okay, because in general, you do not have to calibrate the analog quantum simulator as you will need to calibrate other type of quantum simulators. Also, you study in general extensive magnitudes. and quantities instead of, for example, ground state energies. And that allows you to more or less cancel some errors, at least statistically, okay? But the problem with this is that, as I just discussed, you need to engineer, at least to some extent, okay, the simulated interactions, okay? Why? Because well, the way that these quantum simulators work in a big picture is that what you prepare an initial state, which we assume that it's easy to prepare, okay? You then let it evolve, and this H-cis is the Hamiltonian of the system that you can tune, as I told you, under some extent. Maybe you can do even some fluke engineering or whatever, but you let it evolve, and this is Hamiltonian, that it's more or less fixed, okay? And then after you got your final state, you measure and, for example, compute some ground state energies, some correlation functions, or whatever, okay? And with this, you have done the analog quantum simulator, but you are, after you have disadvantages, you are limited to this H-cis, okay? You need to engineer this interaction somehow. This is a real big difference when we compare these analog quantum simulators with the other approach, which are the digital quantum simulators. Okay, so these digital quantum simulators, what they do is that they implement a quantum circuit, okay, that will ultimately have to decompose in single and 2-qubit gates, okay, and the main advantage of these quantum simulators is that they're universal. Okay, you can simulate any kind of Hamiltonian. For example, here I have a circuit. Okay, if you're not familiarized with this, here is simple a pictorial notation, okay, that we use to denote the qubits. This is a qubit, this is a qubit, this is a qubit, this is another qubit, and the operations that we use to entangle or connect these qubits, okay. And in this case, we can simply combine these CNOT gates, okay, between these qubits, and then this rotation around the Z axis, okay, of an angle delta t, to simulate the Hamiltonian of 3 interacting spins, okay, for a time delta t, okay. So look, this is a Hamiltonian that is acts in 3 qubits at the same time. In nature, this is a hard interactions. It can be obtained somehow in effective ways, but it's hard to obtain without much manipulations. But with a digital quantum computer, we can just create some circuit and we get any kind of Hamiltonian. Okay, this has been actually proved. Okay, so the simulators are universal. Okay, with this you can simulate whatever. Okay, but that big advantage comes with a price, and the price will. Anyway, we have these different type of algorithms, okay, and for example, phase estimation, formulas, quantum walks. There has been a hot topic, and there are a lot of algorithms to use these quantum computers. But as I was just telling you, okay, the price of this advantage is that for most cases of interest, you need fault tolerance. Okay, and what is this fault tolerance? Well, in general, these quantum simulators, these digital quantum simulators, as it happened with the analog ones, they have errors. Okay, so when you use them to perform any type of calculation, you have some errors, okay, under some extent. And the thing is that when we in general, we would like to be able to correct these errors, okay, and this is what we will call a fault-tolerant quantum computer, a quantum computer in which we can correct the errors. This is not easy by any means, okay, but maybe someday we will be able to obtain a fault-tolerant quantum computer, which is fully quantum error corrected. But at least at the moment, okay, well, looking at what we have that current quantum computers are noisy, are also small, and we cannot correct these errors. Okay, so the problem is that although this is really cool, this type of simulators are really cool and are universal, which is an amazing fact. In general, we cannot be sure that the output is actually what we want to obtain due to these errors, okay, which obviously get accumulated as you increase the circuit or the system size or whatever. Okay, so to partially mitigate this, okay, and this connects with the second part of the outline, the variational quantum algorithms, okay, to partially mitigate the impact of these errors, some researchers introduce what we call variational quantum algorithms. Okay, so the idea here is very easy. Okay, is that this is we replace our old quantum circuit, okay, with this parametrized quantum circuit. So what we do is that first, as I told you, we generate a circuit that depends on some parameters. For example, this theta. Okay, this is our circuit that depends on some parameters, and we call this a layer. Okay, and we stack several layers. In this case, we stack D layers. Okay, the same much as happens with, for example, neural networks, deep neural networks. Okay, so we stack layers here, and we have an output. Okay, this output is a quantum state that depends on these parameters. Okay, so we can modify the parameters of the circuit. Hence, we modify the interaction, so we get a final state which is different. Okay, so we first generate this parameterized quantum circuit. Okay, then we use it to generate a certain quantum state, and we measure the output of this quantum circuit. Okay, and we plug this output into a classical computer to calculate a given cost function. Okay, so for example, the cost function can be the energy of certain Hamiltonian. We calculate the expected value of this parameterized state. We get the value of the energy as a function of the different parameters. Okay, I'm sure that most of you know what happens next. Okay, we have a cost function that is already stored in a classical computer. We can approach its minimum using a classical optimizer. Okay, so for example, we can calculate its gradients. Okay, and find a direction in parameter space that is close to the minimum of this cost function. So we can just update the parameters and then plug them again into the quantum circuit, then calculate again the quantum state that it's the output, measure again, calculate the new cost function, and then repeat this process, this hybrid quantum classical loop, until we reach convergence. Okay, and with this, for example, we find the minimum of this cost function. Ideally, we will have the ground state of our Hamiltonian. This is the ground state energy. Okay, the problem is that, well, this is really cool. Okay, and these optimizers help us with limit hardware. Okay, so for example, if we have limit connectivity, if this qubit cannot be easily connected in terms of the hardware with this qubit, okay, and we cannot figure out how some of the algorithms that we discussed before can be applied to this connectivity. Maybe we can just plug a given circuit into this black box with the connectivities that we already have, okay, and then use it to find the minimum, okay, or for example, the optimizer can somehow compensate some systematic errors in the calibration of the device or whatever. So this could be useful for niche devices, for current devices, okay. So just most of the answers that we use in general in current quantum variational quantum algorithms have limit connectivity, they are flash networks or whatever. So this can help us with these problems, okay. But it has been already implemented. Yes, this is probably the first experimental result using the variational quantum eigensolver, which is an algorithm just to find the ground state of a given Hamiltonian. We talk with an actual superconducting processor, okay. But the problem with this is that here they studied a toy model, okay, and as long as you increase the size of the system, which is what we would like to do, you want to obtain any type of quantum advantage, okay, the optimization problem can be extremely challenging. Okay, so just to discuss why this happens, I have here two plots. So this is our accessible space. In some sense, we can, well, our unitary space, in some sense, we can understand this, okay, as the Hilbert space that we want to explore. It's actually the unitary space that create that Hilbert space, but this is more or less for us the Hilbert space, okay. And the Hilbert space the subspace that contains the ground state of your model is here, okay. So for example, you want to find the ground state of a model, and its subspace lies here, okay. For example, this is an excited subspace, okay. So I think is that if you create an ansatz that here in blue that it's able to explore most of the Hilbert space, okay, in general, what you will find is that ansatz is really flat in general, okay. So, okay, you can find its minimum, okay, but it's in general very flat. That means that when you want to calculate the gradients to minimize the cost function, you will find gradients that vanish exponentially with the size of the system, okay. So you need an exponential number of measurements, and hence you cannot obtain any type of quantum advantage with this idea, okay. So you have a really big accessible space, okay. You let that this parameterized quantum circuit explores most of the Hilbert space. In general, you will find these problems, and these have been proven mathematically, okay. These are some of the results, okay. This was the first, okay. Then also they found that this barren plateau problem, as it is called, has to be with the type of cost functions. If you consider cost functions here that are global, you also find these problems. If you add noise, you also find these problems. If you increase expressibility, as I was discussing here, you also find this problem. Okay, so In general, what you would like to have is not an answer that it's able to explore the whole Hilbert space, okay, but an answer that is able to explore a limited region of the Hilbert space that already contains the subspace of interest, okay? So this type of ansatz can be flat, okay, but there are also some type of ansatz that only explore a limited region of the Hilbert space that can be, you know, smooth enough to be trained, okay, and you can find its minimum easily with gradients. Okay, but as I hope to motivate you, I don't want you to be experts in variational quantum algorithms after this seminar. I only want you to understand that, okay, this idea is really cool, okay, but it's not enough for us, because in general, you will have to be very careful designing these parameterized quantum circuits. And even when you got good parameterized quantum circuits, okay, there are not any guarantee that you will be able to actually optimize them, because this is still very hard, okay? So just with this in mind, let me do a short recap, okay? So what we have and what we have been discussing. Okay, so about the question of how to do quantum simulation, we have introduced another quantum simulation, simulators, okay? And we said that, well, the simulators mimic a given target Hamiltonian using a control system. This is cool because you are more resilient to noise and errors, but you also need to engineer the simulated interactions. Okay, and we would like to have something that it's at least up to some extent universal, or at least that you can tune far beyond what you can engineer with your actual quantum system. Okay, so to do this, we turn to digital quantum simulators in which you can simulate any kind of Hamiltonian. But for most cases, they are useless, at least at the moment, because you need fault tolerance. You need to correct the errors. So to correct these errors, at least to some extent, we propose the variational quantum algorithms, which are a quantum classical loop. And here we use a classical optimizer, okay, to help us with the limit hardware. But the problem is that this optimization can be extremely challenging. And in general, these quantum algorithms are useless due to these problems, okay? So up to this point, okay, I don't know if you more or less see the point that I want to reach, but I have been discussing these two approaches, these analog quantum simulators and these digital quantum simulators, as if they were something different. And as a concept, they can be, but we are not limited to consider them as something different. So we may wonder if it is possible to go one step beyond, okay, and say, well, okay, we have these analog quantum simulators, okay, that are more resilient to noise and errors, okay, so compensate some of the errors that these have. But we also have the variational method that can be extremely challenging sometimes, but sometimes works great. Okay, so what about mixing them? What about doing variational analog quantum simulation? And this is the main point of what we do. I want you to understand. The thing is that these variational analog quantum simulators combine the strengths of both approaches. Okay, because first you have the native many-body entangling operations, okay, that we said that these analog quantum simulators already have, and that are more resilient to noise and errors, okay? So we got these native many-body entangling operations, okay? But we include some digital operations to increase the tunability of our system, okay? This is already done in analog quantum simulation, okay? So you combine both of the approaches. So here, our parameterized quantum circuit doesn't have to be, for example, the type of answer that I showed you a couple of slides ago. Okay, we can use, for example, at this unitary, the quantum evolution generated by these many-body entangling operations, the time evolution. Okay, and that can be our quantum operation to entangle particles. Okay, and then we can also include some digital operations here in this unitary, okay, that increase the tunability or the expressibility of our system. And on top of that, what we do is that we include a classical optimization loop that allows us to efficiently use all the quantum resources that we have. Okay, so in some sense, I like this picture, okay, because it more or less summarizes what we want to do in some sense. So we start here, okay? So we are here, this is the Hilbert space, as you can see here. So we start with a given initial quantum state, okay, and we want to reach a given target state. This target state can be, for example, the ground state of this certain type of interesting Hamiltonian. It can be also some state that it's useful for some metrological reason, whatever. We want to go from here, okay, to here, and we have to go through the Hilbert space. Okay, so our tool to travel the Hilbert space is this red line, okay, are our quantum resources that in this sense, in variational analog quantum simulator, are provided by these native many-body entangling operations and also some digital operations. And so this is our resource. And what the classical optimization loop tells us is that, well, okay, you are here, you want to go here, these are your tools. I will help you finding the most optimum way to use the tools that you have, okay? So in some sense, we are not expecting to reproduce exactly the procedure of analog quantum simulation, but instead just saying, well, okay, these are my results. Maybe you, the classical optimizer, can help me to somehow reach the target state that I want to reach. Okay, so there are some works already doing this, okay, mainly with trap ions, which are a very robust platform to implement these ideas, this one, okay. And they do cool things. For example, they do quantum simulation of the Schwinger model, okay, and they find its ground state and they calculate some of its properties. Also, there are some works relating this with quantum metrological applications, okay. But in general, the main thing that that all these works have in common, and will be the challenge that we want to solve with our work, is that these previous approaches consider a fixed range of interaction for the qubits. Okay, that means that you have fixed connectivity. Okay, so they plug this connectivity as fixed in this answer. They repeat at several number of layers, then calculate the minimum, and that's all. Okay, but what we do, and this is our proposal, and if you have to memorize a single thing about our work, I will it to be this. Okay, is that we are motivated by the tunable range interactions that we have when you study quantum emitters coupled to waveguide setups. Okay, and this type of platforms have a tunable range. Okay, and you can optimize more or less you can modify the range of interactions. And we say, well, okay, we can modify this. This is a parameter. So we may also variational optimize the range of interaction. So in this sense, we may also go beyond this fixed connectivity and let the classical optimizer also optimize the connectivity of our system, but always focusing on a natural hardware platform. Okay, something that can be actually done in an experiment in a natural way. Okay, so with this, we replace this analog quantum simulator with our waveguide-QED setup, and what we do is that this general circuit, we generate a waveguide-QED answer we will discuss in a couple of minutes, in which we use there's range of interaction, the length of interaction, and also the time as a variational parameter. Okay, and with this, we come to the first half of the talk. Now we are a good moment to ask any questions if you have any. Okay. With this,
I have a question. Can you go back to the last slide?
Yes, for sure.
I was wondering about the last point you mentioned about the fact that the classical optimization loop allows an efficient use of the quantum resources available.
Yes.
How does this compare to a different system? I mean, what I didn't grasp exactly what does a variational analog quantum simulator special in this point?
Well, that's a really good question. And I think that the most important point here when we discuss variational analog quantum simulator is that we directly use these many body entangling operations. Mm-hmm. Okay, so for example, you can have that your system natively evolves with a Hamiltonian of this form. Let me just show you a Hamiltonian of this form. Mm-hmm. Okay, and you directly let evolve under this Hamiltonian. Okay, so you do not use a specific gate, but instead you say, well, this Hamiltonian obviously entangle the particles, so we just let it evolve under this Hamiltonian and optimize, for example, the length of this Hamiltonian or also the time of evolution or whatever, and optimize the parameters that make this Hamiltonian a unitary, okay, but not angles of a gate or whatever, but instead the direct operation that we know that provides us with this large scale entanglement that is also robust to noise and errors or whatever. So that's more or less the idea, the difference.
Okay, I understand. Thank you very much.
Oh, okay, you're welcome. Okay, so thank you for that question again. And with that said, I hope that more or less I have motivated you what is quantum simulation and why we would like to do quantum simulation and also do analog and variational quantum simulation. And now I would like just to introduce you to the topic of waveguide-QED, just to let you understand more or less what we do and our paper. So in general, the first thing that we would like to do is to, as I just said, discuss like material interactions and then just focus in our results. Okay, so just think about this, okay? So we have two atoms, okay? And this is for a simple situation, we have two atoms and we want them to interact via a single photon, okay? So this is very complicated. I'm sure that most of you know atomic physics, and this is by no means a simple situation. So we simplify it and consider the simple situation. So we model these two atoms as two qubits, okay, with a ground and excited state. Okay, and we want them to interact via single photon. So this qubit is excited, this qubit is on this ground state. So this qubit emits a photon and go back to this ground state. And the thing is that this interaction is very unlikely to happen. Okay, so what happens in general is that this photon travels and gets lost. Okay, this atom is not able to absorb it. So we wonder how it is possible to obtain stronger tunable and coherent interactions between these emitters. And a possible way out is to use light-matter interfaces. Okay, so these light-matter interfaces, in general, they modify the behavior of light and lead to stronger light-matter couplings. Okay, that means that you can tune the coupling between your atoms and light. Also to longer interaction range, because if these atoms interact, that will be because they are very close. As long as you simply put them a little bit far apart, these diffraction limits just simply blow up, and you cannot have an interaction. And also, and this is the most important part, you can tune these interactions that they are coherent. Okay, you can make them not dissipative, at least up to some extent. So example of this is cavity quantum electrodynamics, cavity QED, and also photonic crystal waveguides. I will focus specifically on this second. Okay. With this setup, to obtain these tunable long-range interactions, you need the following. Okay, first you need a waveguide, which can be, for example, photonic crystal, also metamaterial, whatever. And this waveguide simply is a periodic structure. Okay, so here you have the holes that repeat, and since they are periodic, okay, you have a given band structure. Okay, so you have here, you have here the band structure that depends on the wave vector k. Okay, and this is your platform. You use this to obtain the interactions, but you don't have anything to interact. So then you also need to add some quantum emitters, which can be, for example, atoms, but also superconducting qubits or whatever. And these quantum emitters have a ground and an excited state, as we just said, and we have a transition between these states with an amplitude g that couples to a mode k. Okay, so the thing is that we say, okay, we can place the frequency of this transition, okay, in the middle of the bandgap. That means that when we have an atom that is on its excited state and goes back to the ground state, okay, the photon that it emits that has this energy cannot propagate through the waveguide because it doesn't have the low energy. Okay, so the thing is that this photon, in some sense, gets bounded to the atom, cannot travel through the waveguide, okay, and gets bounded. And this is what we call atom-photon bound states. And with these atom-photon bound states, okay, we have the atom, we have a photonic cloud, and we can obtain these effective interactions by means of these photonic clouds. Okay, they overlap, and this overlapping kind of dictates how the atoms interact. Okay, you can also include some lasers to the atoms, to each of the atoms to increase the tunability. So, for example, you can couple the E state to a metastable ground state S, okay, and you can adiabatically eliminate them to obtain an effective interactions in which you can tune the amplitude of interaction using the laser. You can dynamically tune them. So this is very, very tunable indeed. And the type of Hamiltonians that we reach, as I just told you, are Hamiltonians of these ones. These are the ones that we study in our paper. Okay, so that, for example, XX type of interactions. Okay, can be also this is a sigma plus sigma minus type of interaction, and also you can obtain Ising type of interactions. And the thing that I like the most about this, and this is probably the most important thing concerning the physical platform that we use in this paper, is that here you can see that the interactions is all to all. Okay, it's not first neighbors. Okay, we don't have I and I plus 1. We have I and j. The only thing is that the amplitude of interaction decays exponentially with the distance. But for example, if L is very big compared with the total size, okay, we have almost effectively an all-to-all interactions. And if L is very small, we have effectively a first neighbors interaction. Okay, so with this parameter L, which can be tunable and can be tuned, for example, with the tuning of some laser and some transition, okay. Tuning this parameter, you can tune the range on the interaction. And this is very cool, okay? Because we can, as I just told you, we can use this range as a variational parameter, Okay, but just before considering this, let me just go a little bit briefly through the maths of the thing. Okay, what we do to obtain these Hamiltonians from these complete models is that we project the dynamics into the slow ground subspace. Okay, this is a procedure that it's typical in the quantum optics literature. So we have a multi-level quantum emitter that has slow and fast subspaces, okay, and the dynamic here are so fast that we can somehow neglect them. We can forget about this fast subspace and include its effects as a perturbation in the ground state Hamiltonian. Okay, so we have the slow and the fast subspaces, we have the transition operators, and we have some jam operators that induce losses, and we can effectively project the dynamics over the ground subspace. Okay, this is what we do. Okay, these Hamiltonians are simply the calculations or the ones obtained once you project the whole dynamics of the whole Hilbert space over the slow subspace. Okay, so with this in mind, we get these models. Okay, more or less, this is the idea. We get all this set up, and at the end of the day, under some approximations, we finally reach models of this type. Okay, and with all of this, we build our waveguide-QED answer. Okay, which is the one that we compare with other types of answers usually used in a variational quantum simulation. Okay, so the ingredients to obtain this answer is that we first left our system to evolve freely under the interaction Hamiltonian, which are these two types. Okay, we consider XX and we consider icing. Okay, in two different cases, and we let time and length. Okay, the total time of interactions and also the length of the interactions as variational parameters. Okay. We also include some single qubit rotations that increase the expressibility somehow, and that leads us to our waveguide-QED variational answer. Okay, so we have here the waveguide block that entangles the qubits, and then we can include some single qubit rotations, and we stack the layers. Okay, and at the end of the day, we measure, we calculate the cost function, and we repeat the procedure as we just discussed before. Okay, what we do in our this first paper is that we use this waveguide-QED answer to find the ground state of different short-range spin models. Okay, so for example, the XX set or the icing model. Okay, but most of you know, and we benchmark, okay, the accuracy of our calculation using the fidelity between the optimized state and the actual ground state that we can calculate numerically easily because the systems are very small. Okay. And then we compare our results with the state-of-the-art ansat, which are, in this case, the hardware-efficient ansat and the bricklayer ansat, which use single qubit rotations and control set. Okay, so this is a very naive ansat. Okay, that works really bad. You will see it, but it has been used in the literature. This is an ansat that, in some sense, remember an MPS. Okay, so it works more or less great for this type of systems, but also under some conditions. There also this Hamiltonian variational ansat that works really good. Okay, also in some cases. And we also consider an infinite range type of interactions, which are simply these interactions, but taking L going to infinity. Okay, just to see if the effect of variational optimized L has to be with the good results. So with just this, let me go briefly to our results. Okay, the first that we did, as I was told you, was studying the XX set and the icing model. Okay, and we studied the infidelity of the quantum states as a function of the depth of the field weight at the critical point. Okay, these models are critical, as most of you know, so we study them at the critical point. And the thing is that what we see, okay, this is more or less our results. Okay, and here we see the following. Okay, we see first that the hardware efficient ansat had the worst performance, as you can see here. Okay, in general, this hardware efficiency is really bad. This is in agree with what we expected, because this type of ansat does not have any type of structure, so it finds a lot of Barron plateaus and it cannot be trained in general. Okay, then the bricklayer ansat, as you can see, especially here, okay, was good, but only after a certain depth. There's like a phase transition here in the accuracy. Okay, and this indeed has been found, and it was expected, and it has been extensively discussed in the literature. Okay. Okay, this means that, as you can see, these ansat reach good fidelities, for example, 10 to the -4, but you need to stack a lot of quantum operations. And in general, this will not survive when you include noise. Okay. Then, when we go to the Hamiltonian variational ansat, okay, the Hamiltonian variational ansat is an ansat that generates a quantum circuit using the unitaries generated by the terms that do not commute in the Hamiltonian that you want to study. Okay, so you get your Hamiltonian, your Hamiltonian generate this type of red blocks operations, and you just stack them. Okay, so in some sense, your quantum circuit resembles the type of systems that you want to study. Okay, and this has been extensively studied and it works really good. But the problem is that although it works good, as you can see here, you need some depth to reach good results. Okay, but the thing is that now when we go to the waveguide-QED answer, okay, what we find is that okay, our waveguide-QED answer works really good. Okay, but it especially works good at short depths. Okay, in some sense, okay, what we have is that since we can variationally optimize the range of interactions and the distribution for each of the layers, okay, we first generate as some state that it's very entangled, okay, and then with the next layers, we're able to correct this state to finally reach an accurate ground state, okay, with just a few number of layers. Okay, in particular, we study the minimum depth to enough fidelity above 99% as a function of the number of qubits. This is for the XX set. This is for the transverse file Ising model. You see that if in general, okay, we need much less layers and much less minimal layers to reach good results with the waveguide-QED answer than with other types of answer. Okay, and if you also focus on the infinite range case, just as a comment, note that this works really bad. Okay, so that means that the optimization of the range of the interactions also has to do with these good results. Okay, however, this is only first neighbors. Okay, the thing is that we have long range interactions, so we may wonder, okay, is it possible to go one step beyond and study long range model, which are a natural playground for this type of systems? So what we did is that we extended the first neighbor as a model to its long range versions. Okay, so we have the same type of model, but here the interactions are long range and decay polynomially with the some value alpha. For each of these alpha, we have different value of theta crit that leads to a critical phase. These models are critical, so we also study them in their corresponding critical phases. Apart from all the things that I just told you, we also include a combination of exponentials, okay, as a new answer that build a power law interactions. Okay, so when you have sums of this type, you can optimize these parameters and up to some extent, okay, to obtain a power law interaction. Okay, so in these cases, this is an HVA for this model. So we also include this type of interactions which are long range, okay, but cannot be dynamically tuned in these cases. Okay, and what do we find? Okay, we studied 3 different regimes. In the first one, which was alpha equal to 1/2, this is a very, very long range model. And what we see here is that the power law, which is here in green, in general outperforms the waveguide-QED answer. This is expected since, on the one hand, the power law is an HVA, so we know that they work really good. But on the other hand, this type of HVA also has long range interactions by itself. Okay, because here alpha is small, so hence this is a long range interaction. Okay, so this HVA works great because, as I told you, first it's an HVA, second it's long range. When we go to a medium range case, okay, what we find is that, okay, again, the power law works great, okay, but it doesn't work as great, especially when we go at short depths. Okay, at short depths, the waveguide-QED answer wins. Okay, so that means that the possibility to being able to dynamically tune the range of the interaction has an advantage, especially when you have short depths. Okay, just a brief comment. Okay, you take a look at the long range interactions, but the infinite range, but we have been able to optimize the parameter, the L going to infinity case. Okay, you see here that it soon reaches a plateau, and this plateau is worse as long as you increase you decrease the range of interaction as expected. Okay, and finally, what happens in the alpha equal 3 case, which is a short range case, is that the waveguide-QED answer in general outperforms the power law case as expected here, because here the power law is simply an HVA, it doesn't have the effect of being long range. Meanwhile, the waveguide-QED answer can still exploit these long range effects. Okay, so more or less in summary, we see that this classical optimizer allows us to exploit the tunable long range. Okay, and we can use it to generate the desired state with less resources, in this case, with less layers. And this survives, I only want to discuss this briefly because I have no time, but this survives when we include noise. Okay, so these results are for noisy simulations, okay, are results in which we consider a realistic model of noise. And when we consider noise, okay, and include some probabilities of error in the single and 2-qubit gates, we see that in general, the the bricklayer answer that were good, okay, in these other cases, okay, now are really awful. This is because you need a lot of quantum resources to effectively implement a bricklayer answer. And what we get is that our waveguide-QED answers, okay, still survive like the best, because you are using shorted circuits, but you are optimizing these shorted circuits, and you are using all the possibilities all the possible resources that you have, okay, with your classical optimizers. So with this, I more or less come to the end of the talk. Okay, so I would like to wrap up some conclusions to give you a take-home message. The first thing that I hope that to have combined to you is that variational analog quantum simulators are a promising approach to obtain this practical quantum advantage. Okay, in general, we would like to obtain this practical quantum advantage in quantum simulation, because it's a natural playground for quantum computers to work. Okay, and in particular, analog quantum simulators work really well, and we have a lot of quantum coherent resources here. And with a variational optimizer, with a variational method, using a classical optimizer, we can exploit these resources in some sense. So this is the main idea that, or a good candidate to obtain a practical quantum advantage. In particular, what we have is that in this type of analog quantum simulators, the waveguide-QED platforms offer tunable long-range interactions, and this can be exploited as a resource to improve current quantum algorithms. Okay, we have actually found, considering our results, that these interactions can help us find the ground state of critical speed models using less resources, in this sense, less number of interaction gates. Okay, so this is especially useful when we include models of noise. And finally, just as a connection with other type of platforms, we see that this type of results can be extended, for example, to trap ions or prepared atoms, that are platforms that already have long-range interactions. And in particular, in trap ions, they're expected to be tunable, okay, too. So you have models following the long-range transverse field Ising model that we just discussed. So this type of conclusions and this type of results could be also extended to these platforms, although they were already initially motivated by waveguide-QED setups. So with this is my group. These are some of the collaborators in which I've been doing this work. This is our preprint. So you want to take a look, you can just scan this QR code or just put this in Google. That will be all for my part. Thank you for your attention. Thank you.
Thank you. Okay. Okay, there is something wrong with my microphone, and I don't know exactly.
Technical problem.
Okay, now? Yeah.
Yes.
Yeah, fine. Some resonance with Guillermo. I don't know exactly what happened. Okay. So if there is any question from the audience, you can just unmute yourself or write it down in the chat. Okay. Well, if no, I will start. Well, thank you for the presentation. It was really nice. I enjoyed it a lot. The first question is, okay, I would like to know is there any estimation of the amount of error, and for instance, in your infidelities that may be induced by losses or decoherence, specifically in waveguide-QED simulators, compared, for instance, to another analog quantum simulators?
Well, the thing is that, in particular, let me just share again, and let's see, just to point out you some references. Okay. In particular, here is here. Okay. What they do is that they analyze the errors between digital quantum computers and analog quantum simulators in general. Okay, so they consider a naive model for an analog quantum simulator, inspired obviously by ultra-cold atoms, and also to some extent by trap ions. Okay, and then under that model, they compare, and they more or less find that current quantum simulators. Okay, there are some experimental people, this for example Claude and people like that. And under some conditions, current quantum simulators are as good as fault-tolerant quantum computers will be. Okay, but that is for trap ions, in particular for waveguide-QED setups. We have not at the moment discussed or study the topic in detail. This is just a first work. The thing is that, well, I guess that your question is motivated by the type of dissipative behaviors that you can have in waveguide setups, right? The thing is that, well, let me just stop sharing the screen. The thing is that we have been thinking a little bit about that, and indeed you have dissipative evolutions in waveguide setups, but they shouldn't be something negative, at least if you think about them under some extent. But that would mean to introduce a setup that is completely different to the one that we're doing here. Okay, so here our noise model is a very toy model. Okay, and we have not yet benchmark it against the other type of platforms. Obviously, yes, you have that. In general, the cooperativities in current waveguide setups are very small compared with what they could be. And also, when you want to compete against, for example, trap ions that have fidelities in 2-qubit gates that are astonishing compared with waveguide setups. At the moment, we cannot compete against them with realistic setups. But the thing is that, in general, we would like to point is that waveguide is an inspiration. But what I find interesting in this work is that we have a resource. Okay, this means that, for example, we can use the range as a resource in these analog quantum simulators, and that is not specifically focused to waveguide because it's an inspiration, but it's also focused to other type of platforms. That thing, I think that's like the most important relevant feature of this work.
Yeah, I agree. It's a great result. So okay, thank you. Is there any other question from the audience?
Yes. Can you explain a bit more for your waveguide-QED model?
Yes.
I understood that you adiabatically eliminate the fast degrees of freedom or the highly energetic degrees of freedom. Those are the waveguide modes, essentially.
Yes, essentially, and also, well, in general, when you want to do this, you can use, for example, superconducting qubits or atoms, and you also have an excited subspace in your qubit. Okay, for example, in atoms, you have another hyperfine manifold. In superconducting qubits, you have this anharmonic ladder, and you just consider the two states on the ground subspace, okay, as your slow subspace, and you automatically eliminate first, as you said, all the photonic states, but also the excited states of the qubit.
Okay. So you don't start from a two-level system, but you also eliminate the higher energy levels of the system and end up with two levels.
Exactly. For example, if you take a look, let me just share the screen again. If you take a look, okay, at this, let's see. Oh, okay, give me a second. I think that you cannot see my screen at the moment, right?
I cannot.
No.
Now, yes, right?
No.
Okay. If you take a look, for example, at this configuration here, okay, what we do is that we have 3 levels. We consider 3 levels in our quantum emitter, okay, apart from all the photonic states. And what we do is that we couple this E state to an S state using a laser, and also we couple this E state to the G state via a radiative transition. Okay, and the thing is that we automatically eliminate this E state. Okay, so we obtain an effective qubit concerning these G and S states. Okay, and this transition from the S to the G state populates this E state virtually. So by means of this virtual transition, okay, you can tune the amplitude. So in general, we include things, yes, and we eliminate all these things just to have a qubit, but with a tunable control.
Okay.
Thank you for your question.
Okay. Is there any other question? Okay, so it looks like we don't have any other question. Okay, so if that's the case, Cristian, thank you very much for your seminar. It was excellent. Thank you all, and see you in the next seminar.
Thank you, guys. It's been a pleasure for me. Have fun.